Everybody for attending today's ETP session for heat heat energy theme session, and welcome to attend this discussion to present your research progress. And the first presentation we are going to hear is from Ahid Elteby from University of West of Scotland. The title of his presentation is Modern Heat Transfer Fluids Developed Using Nanochemistry. Welcome, and please start your presentation. Thank you.
Thank you very much. My name is Ahmed Eltayeb. I am a PhD student in University of West Scotland. I'm here today to talk about nanofluids and improving the heat transfer characteristics of water. To the project objectives is to investigate the treatments to alter the thermal characteristics of water and establish optimal treatment for water that can improve the heating and cooling in buildings, especially in buildings. This will involve looking at treatment containing nanoparticles, also surfactants and other organic molecules, additives on water. The project also is looking for using these heat transfer fluids in heating and cooling, other heating and cooling applications, such as in car radiators and electric vehicle battery cooling and computer stations. The main benefits of this project, there is a huge energy consumption for space heating and cooling. In the UK, it's was estimated by the government, it's about 41,000 million ton oil equivalent. If assuming this is 90% of this is for heating houses using water systems, it will be a very large energy saving if we can increase the thermal conductivity of water in this system. This involves the formulation of water-based heat transfer fluids. All this for that everybody knows that UK is heading toward net zero. As the UK is heading toward net zero by 2050, excluding the transport energy consumption, is 78% of the energy is used for heating buildings and domestic houses, offices, schools, factories, hotels, and other buildings. This is a government statistics. As you see, the space heating, the domestic space heating is the largest amount. We're talking about 85%, and the services, the heating of the surfaces is much lower. Excluding the transport industry, 78% of the energy is used for heating. There is a product on the market from a company called SafeSol, which is my founder for the PhD also. They sell SafeSol Delta T product. This product is formulated from water-based formulation for the heat transfer in buildings, and has a very good efficiency, about 15% savings on energy. The Delta T formulation is based on surfactant only. It's not based on nanoparticles, only surfactant. The energy is 15% savings, But I have heard a lot of engineers that they, as the product is very new and is not known everywhere, the people, they don't believe this energy saving will happen. So I'm here to let you see by evidence that this energy saving could be very useful. As we know, the heat transfer fluids is used in many applications, such as battery car, electric vehicle cooling system for the batteries, and the car radiators for heating of buildings, offices, and other buildings. Also, as solar panel heat transfer fluid. By searching on Google Trend, by searching nanofluids, I found that a huge interest in nanofluids in the world. And this interest is focused in Iran. I wondered why the nanofluids is very interesting, very interesting for Iranian people. I searched in the literature. I found that nanofluids are used in heat transfer in nuclear reactors. The interest in nanofluids with the heat transfer, especially with heat transfer, is trending on Google from 2004 to 2021. Is increasing the interest in nanofluids as heat transfer fluids. For the number of documents published is increasing as well since 1993 until 2020. The number is increasing as you see the trend. The most published papers is the heat transfer characteristics of interested in heat transfer characteristics of nanofluids, as you see from the bottom right graph. Nanofluids are simply based on a base fluid, which is could be water or ethylene glycol or other fluid, and nanoparticles floating in it. The nanoparticles could be different, could be metals, could be metal carbide, could be metal oxide with the size less than 100 nanometers. As you see here, the upper right photo is for titanium dioxide nanoparticles in water. And the upper left photo is for zirconium nanoparticles. The lower left photo is for to explain the nanoparticles, the nanofluids. This the left bottle is glass beads with 1 centimeter diameter, and the right bottle is the same material, which glass, with the 50 nanometer size. So the beads here is not able to float in the water, but here, as you see, the nanofluid is suspension. Are nanofluids good for heat transfer applications or not? This is the question, the research question. Here, the enhancement of thermal conductivity happened to nanofluid. As you see from this the graph. This is the thermal conductivity ratio between the nanofluid and nanofluid divided by the base fluid against the volume fraction or concentration of the particles. Using ethylene glycol plus copper oxide, as you see, the thermal conductivity increases. Ethylene glycol plus aluminum oxide also. Water plus copper oxide, the same, is increasing with different slopes. Water with aluminum oxide also. The ratio between the nanofluid and the base fluid, because the base fluid, the thermal conductivity of the base fluid, such as water and ethylene glycol, is very low. We're talking about the water is 0.6 and ethylene glycol is 0.2. While the aluminum oxide is 40. Packing the water with aluminum oxide or copper oxide increases its thermal conductivity. These graphs is for aluminum oxide nanofluid. Decreasing the size of the particles increases the thermal conductivity. Decreasing the size of the particles and also the concentration of the volume fraction affects the thermal conductivity as well. And this is different sizes with 5 nanometer, 50 nanometer, 25 nanometer with different volume fraction of aluminum. While the other side is the copper oxide with different also different sizes and volume fraction. And as we see this, there is a significant change in thermal conductivity. To measure the thermal conductivity of fluids, there is a very common method called transient hot wire method. The thermal conductivity measurements of fluids, there is many different methods in this graph, as you see: cylindrical cell method, temperature oscillation method, steady state parallel method. I have chosen the transient hot wire method because it's the most used and reliable also. These are photos of my experiments. Because I am interested in the thermal conductivity of nanofluids, I had to build the device. And here is the circuit. The circuit that senses the electrical resistance of the hot wire. Oh, sorry. Oh, sorry. The electrical resistance of the hot wire. The hot wire here, the transient hot wire, and this is attached to a circuit which recovers a signal from the hot wire, and there is an analog to digital converter to sense the signal. I had this design from the first experiment, and then I changed the design to this one with the hot wire inside here. I don't know if you can see it. It's 50 micrometer. It's very thin. After having the circuit, the electrical circuit done, I had some problems with the electrical circuits from the wireless communication. You have the signal embedded inside the signal from wireless communication. So I'm trying to build the circuit on PCB using a PCB software in order to avoid having too much noise in the signal. This is the PCB that I have built. I've printed it as well. From the front and this from the back. And this is the wiring inside. Instead of making wires, the wires are built in the PCB inside. I had the signal from the analog to digital converter here, voltage against time, but the signal is I still have to improve the signal and filter it because it's a little bit emptied inside some noise. And I'm trying to do that. To explain the effect of the thermal conductivity in heat transfer, I'm going to show you some computational fluid dynamics simulations. These computational fluid dynamics simulations is done for water and ethylene glycol, also glycerine, also in a heated tube with the same inlet condition and wall temperature. Here, the upper right simulation is for water. And as you see, the condition is the same for all of them. So the water at the outlet, the temperature diffusion is much higher than the ethylene glycol and the glycerine. The glycerine and the ethylene glycol is nearly, the thermal conductivity is fairly near, is 0.25 and 0.29, while the water is 0.6. So the thermal conductivity affects the heat conduction too much, really. The summary of this, that the heat transfer fluids, the nanofluids and the heat transfer fluids can decrease the heat, consumption, the energy can decrease the energy consumption, and as I said, there is in the market some fluids such as Cefsol delta T, which are already in the market and is used for many buildings. The CFD simulations can help to decrease the cost of the experiments and provide trusted results. And as you see, by increasing the thermal conductivity of water, the heat transfer efficiency will increase. So we are trying to formulate the best nanofluid to be used in buildings and as a heat transfer fluid in buildings, in electrical vehicle cooling, computer stations cooling, and other applications. I would like to thank everyone funded this PhD, especially the University of Scotland, Cefsol, and Home Technology, and my supervisors, Professor Mohammed Yassin, Professor Mustafa Rateb, Professor ZP New, and also Mr. Robert Wilson. Thank you very much. Thank you for listening.
Thank you very much. Thank you for your presentation. Very interesting.
Thank you very much.
There's a couple of questions from.
Yes, please.
I read it from Lian. The first question she or he mentioned. I may have missed this, so apologize. How did you measure the size of nanoparticles? Was AFM or SEM used?
Actually, I didn't reach this. I'm building the device now, but there is many methods to measure the size of the nanoparticles. Where's the question? Where's the?
Okay, you didn't use
Yeah.
the micro, so you didn't measure the size of them.
I didn't prepare yet the nanoparticles, the
You-
nanofluids, but I'm building the instrument now.
So you mentioned that you have built 2 test rigs to measure the thermal conductivities. Why you designed the second generation of the thermal conductivity rig? What's the difference? What's the advantage of
The
using?
advantage of what? Again, please. The question, please. Yeah.
What is the advantage to use the second generation of the thermal conductivity testing rig? You mentioned that you have 2 rigs in the PowerPoint.
The CFD simulation.
No, experiments rig. You said you measure the thermal conductivities using your self-designed experiment rigs.
Yes.
Why you design 2 of this one?
Because it's very expensive, so we were trying to design it to make it.
So what's the advantage of the second generation? You mentioned a pipe, using a pipe, which is smaller size compared to your first generation of rig. Why you design 2 rigs doing exactly the same thing?
No, sorry. This one, this slide.
You didn't share. Have you shared your slide?
I'm sharing. Yeah. Okay. 1 second. This slide.
Up.
Okay. This one. This one.
Yes, you mentioned that the third picture. So you have 3 pictures.
Yes. Okay. This is the hot wire. It's too difficult to see. It's very thin. Okay.
Okay.
The wire here is not in tension, so this will affect the measurement. But you can see it because there is a spring here. Is putting the wire in tension to avoid that the wire here is not in tension, as you see, is not. It will affect the measurement.
Okay, you do some improvement in the second generation.
Yes.
Okay. What is the results from this testing? You only present a picture of the voltage.
Yes.
What is the main results? What material you have tested?
Water.
You only tested water.
Water, yes, because
no nanoparticles, no any nanoparticles.
Not now, no, because I need this this signal to be smooth first.
How can you validate the results using the CFD model if you haven't got the results from the nanoparticles?
No, the CFD has been done on fluids that the thermal conductivity is known.
The thermal conductivity is known. So the rig you design is only to measure the thermal conductivity of the water to demonstrate that it can be useful, isn't it?
Yes.
Okay. So you didn't test this safe soil delta fluid. You didn't test
no, not now, no. I still waiting to improve this signal.
Okay. Did you validate your results from the CFD model?
No.
You didn't validate the results. Okay, thank you very much. I guess we have to go to the second presentation. Thank you very much for your presentation.
Thank you very much.
Now we have our second presentation entitled "The Injection of Green Hydrogen into a 2D natural gas reservoir," presented by Ricard, I think. No. Presented by Maria Isadi, isn't it?
Hello, can you hear me?
Yes, I can hear you. We are from Edinburgh Napa University. Welcome.
I'm from University of Glasgow.
Oh yeah, I think the ranking of the presentation is wrong from my what is the title of your submission?
Defrosting air source heat pump.
Oh, defrosting of air. So the ranking of the word file is, the abstract is different. So welcome. Your presentation will discuss a review on the defrosting of air source heat pump, and presented by a PhD student from University of Glasgow, Maya Isadi. Oh, sorry, I may pronounce wrong for your name. Please correct me. Welcome, and please start your presentation. Thank you.
Thank you for your introduction. Hello, everyone. I would like to present to you today a review of defrosting air source heat pump and the method that have been studied so far in the research. So what's a heat pump? A heat pump is a thermodynamic device that will extract heat from a cold source to discharge it in a hot sink. And doing that, we can provide heating or cooling depending on the demand. Heat pumps are a known device already and are seen as the key factor to decarbonize the UK heating sector, which is the most carbon emission one. For the International Energy Agency to reach net zero goal by 2050, we would need to install 600 million heat pumps in the world by 2030. And as for today, we are only below 200 million of heat pumps installed for heating, which only met 7% of the global building heating demand. So we have still a large gap to fill before reaching that goal. And what we ask is why heat pumps are not democratized yet, because it's a known technology. And if we see some study, we can see that 90% of the world could use air source heat pump, which is a type of heat pump using air as the heat source. This is the simplest type of heat pump you can install. This is also the cheapest one, and that could be worldwide use, but it's not because for cooling application, most of the time we don't have issues, but for heating application in some cold region, we will have an issue with frosting, which is a problem for the heat pump efficiency. And as we can see here, frosting is something that will happen on the evaporator, which is outside and is in contact with ambient air. So during like cold winter, or when we have a high level of humidity in the air, the heat pump heating capacity will drop, and we can even reach a heating capacity of less than 30% in less than an hour, which will consequently make the coefficient of performance, so the COP, drop. And the COP is the ratio between the heating capacity of the heat pump and the power consumption, which will consequently as well make the seasonal coefficient of performance drop. And the seasonal coefficient of performance is just the average of the COP throughout the year. And that can be an issue for marketing heat pump. Why? Because, for example, in the EU, we need a minimum of 3.8 SCOP to sell a heat pump, an air-to-air heat pump. And to sell an air-to-water heat pump, we'll need a minimum of 2.8, roughly. So that's a challenge to overcome to make a heat pump more air source heat pump, particularly more worldwidely used. And now, when a frosting happened, I said it was during cold winter, in cold climate in general. So when the ambient air is below 6 degrees and we have humidity higher than 67%, then we can see frost forming on the evaporator. And we got a maximum rate of frost when the temperature is 0 degrees and the humidity is at 100%. And mostly what creates the frost is the humidity. So the higher the humidity is, the more critical the frosting is. So what has been done to try to overcome this burden? Some try to remove the moisture from the air because the humidity is the most critical factor. So removing the moisture from the air will avoid frosting on the evaporator. So what we could do is put a solid desiccant or put a liquid one, which has been tried, just before the evaporator. So when the inlet air go through the solid desiccant absorbing bed, for example, moisture will be removed from the air, and we only have dry air going through the evaporator, avoiding frosting. Now it's very useful to keep the heat pump frost free for a long time, and that would definitely increase the heat pump efficiency. However, it's very costly, and the structure can be very tricky to put in real life situation. Moreover, the desiccant is efficient as long as it can absorb moisture from the air. So at some point we will have to regenerate the absorbent bed, which can be energy consuming depending on how you would do that, and that can take a lot of time during which the heat pump can still frost or will be turned off, which will affect indoor air. Now you could use wasted heat or solar energy to regenerate your desiccant, but that will make the structure even more complicated and the application even more hard. What has been done as well is, if we can't remove moisture from the air, then we will try to delay the defrost, making the heat pump efficient for a longer time. So what has been tried is to heat ambient air, because increasing the air temperature will avoid frost from forming in certain conditions. So what has been tried is to put a heater just before the air reach the evaporator, and that would delay frost for a while. What has been done as well is to turn off some part of so we divide the evaporator in two parts, and we will have two inlets of the refrigerant. So we will just cycling off both parts. So if this part is frosted, then we would just turn off this inlet and let this part defrost while the other one is still provided in refrigerant. And what that will allow is to keep heating with one part of the evaporator while the other one is defrosting, and that would delay frost for a while, and you can still use the heat pump. What has been tried as well is to heat the refrigerant, so you just add it to the cycle, which will increase the temperature of the outdoor core, and therefore less frost will form. What has been tried as well is to use ultrasonic vibration, so you just use mechanical force to make the frost fall on the ground. And all those techniques can be efficient at some point, but we will still have some disadvantages. So for example, for the first one, that can only be done for small capacity heat pump, because the electric heater will be very consuming of power. So if you use the heat pump to heat indoor air and you use an electric heater to heat the air to avoid the heat pump from frosting, you will lose it in efficiency. And cycling off the evaporator work for a good amount of time, but the issue with that technique is that when the temperature is below 0 degrees, then the frost won't melt, so that won't work at some point. What else? Heating the refrigerant causes the same issue, because increasing the temperature of the outdoor core works until we reach a certain temperature of ambient air, for which frost will still form. And that's for the ultrasonic vibration. The issue is that you can break the early frost layer of the frost. but the thickness of the frost will still increase with time because you can't remove all the frost with that technique. So what we can conclude is that over time, we still need an efficient defrosting technique. So what has been done to defrost heat pump, we try to spray hot water on the evaporator. So that works. That's an efficient way to remove frost, but we'll see why it's not as efficient as that. And now what has been done as well is to just turn off the compressor. So you just turn off the heat pump basically and blow. Here you can see blow air on the evaporator, hot air as well, so that the frost will melt. While there's electric heating, it's a common technique to defrost heat pump. So you just put an electric heater next to the evaporator and let the frost melt. And the two last one are the most used technique for high capacity, I mean, not small heat pumps, but medium-sized heat pump, which are hot gas bypass and reverse cycle defrost. So hot gas bypass is during a normal heating cycle, the refrigerant will go from the compressor to the condenser, expansion valve, evaporator, and back to the compressor. And when you want to defrost your heat pump, you just put a valve here, you turn it on, and that would bypass the hot gas from the compressor to go directly to the evaporator, so you can provide heat to the evaporator to melt the frost. Reverse cycle is putting a reverse valve here, so that when you want to defrost your heat pump, you will just use the evaporator as a condenser and the condenser as an evaporator. So now the gas will go that way on the right and go through the evaporator, the expansion valve, back to the condenser, and then back to the compressor. All those techniques have their advantages, but they also have issues. So for the first one, the most obvious issues is that it's very long, and during the defrosting cycle, the heat pump is turned off. So if it's very long, you can't provide heat to the indoor environment for a long time. And you need to blow hot air for the frost to melt. So you also need another heating system for heating the air you're blowing on the evaporator. For the hot water spray, the defrosting time is quite low. So that's a good thing, but the issue is that putting water on the evaporator would just enhance future frost formation, which will increase the need of defrosting over time and decrease the efficiency of the heat pump. And the hot gas bypass and reverse cycle, because those two techniques are the most used, they have been compared a couple of times. And what we can conclude is that the reverse cycle is they take less time to defrost the heat pump, for the simple reason that you can use two types of energy sources while doing the reverse cycle. So you get heat from the compressor, and then you can also use heat from indoor air or the water you heated. But the issue is by doing that, you will alter the indoor thermal comfort. So we just extract heat from the place you just gave heat before that. So that will be very complicated to make it beneficial for the user if the need of defrost is very important. So what has been done to try to improve the defrosting performance so that it lasts less time and alter less the thermal comfort of the user? So we tried to put a different type of compressor and see the impact on the COP. They tried to put a hydrophobic fin on the evaporator, and we can see that it shortened the defrosting time. What has been done as well is to try different type of expansion valve, and the most efficient so far are the electronic expansion valve that will increase the efficiency. We tried different type of evaporator structure, and it can be concluded that the horizontal installed evaporator increased the defrost efficiency, and lastly, different type of control measure has been done. And monitoring frost levels really show an increase in the COP of the heat pump, because if we monitor frost level correctly, then we will need less defrost cycle. And despite all of that, we still need to resolve the issue while doing the reverse cycle. Because if the hot gas bypass and the reverse cycle are the most common used techniques, the reverse cycle is the most widely used. And the issue with that defrost technique is that you take heat from indoor. So we have a lack of energy approvisionment in the system, and techniques have been tried to put a thermal energy storage inside the heat pump system to avoid taking heat from indoor here. And about thermal energy storage, we can see three main ones: sensible heat storage, latent heat storage, and thermochemical storage. And the first two have been tried and have been investigated for a use inside the heat pump cycle. So with sensible heat, we try water tank, which is the most known one. And a technique has been tried to charge during the day a water tank and with a heat pump. And during the night, when the temperature dropped and the humidity of the air was higher, the water tank would discharge its heat to heat water inside the house. And for latent heat storage, phase-changing material have been widely investigated to put inside a heat pump cycle to store heat during charging. So on that system on the left here, you will have, during the heating cycle, the refrigerant flowing through the indoor coil, normally then being expanded here with the capillary tube and going to the evaporator and coming back to the compressor until, so we would monitor the temperature inside that we're trying to heat. And when we reach that temperature, then we'll just turn off that valve and the heat will go, the refrigerant will go to the PCM to charge it until it reach its melting point. And then we will turn on that valve again. And when we need defrosting, what we'll do is just turn off that valve so that the refrigerant doesn't flow through the indoor coil, and we reverse the cycle. The refrigerant will then go to the evaporator to defrost and back to the PCM to be used as an evaporator, and then back to the compressor. So we never extract heat from indoor, and that's better for the user, obviously. And what has been tried as well is to store heat. So we don't put the PCM inside this, we put the PCM in the cycle, but we don't charge it with the refrigerant. So what we've done is, what they've done is to put a PCM just around the compressor casing, and it will charge by using the heat dissipated by the compressor by conduction and convection. So during a normal heating cycle, the cycle is still the same as usual. And when you want to defrost, you'll just turn on that valve F1 and F3 and turn off the valve F2. And the refrigerant will flow through that pipe here. And here it will be divided in two different flows. And what we'll have is like one part of the refrigerant will still go indoor and heat indoor air. And the other part will go to the outdoor core to melt the frost. And then both flow will be expanded here by the capillary tube and here by the electronic expansion valve. And then they will be mixed in the valve F3, go back to the PCM. The PCM is then used as the evaporator, and then back to the liquid gas separator and to the compressor. So now that technique is very efficient for one thing, is that you can still partially provide heat while defrosting, which is a really good thing, and that has never been done before. And that will also reduce defrosting time. So the PCM always reduces the defrosting time because we can extract more heat from the PCM than what we could from indoor air without really affecting indoor air. So that's a promising future for thermal energy storage. The issue is that it can be very costly. I mean, so far it's costly because it's not very widely produced. So we have to be careful in what type of PCM we will use. And for the first study, they have concluded that the additional add of the PCM will increase the cost by around 30%. And another problem is that the power consumption during defrosting has been increased compared to a normal reverse cycle. The issue with that is that, I mean, it's an issue because the power increased, but the defrosting cycle is shorter. So globally, the consumption of the heat pump didn't increase and the COP still increased. But the issue is that if you have to defrost a lot of time, then at some point you will have less improvement in the COP. So what can be concluded by that is that thermal energy storage incorporated inside the heat pump cycle is a very promising technology, and further investigation could be done with that. And that's what my research will be about. And mostly we will focus on trying to find a simple way to integrate the thermal storage in the heat pump without increasing the price of the heat pump to a too much high price. And what else is to work on the reducing of the power consumption while using a thermal storage, which will increase the COP and the efficiency of the heat pump. And by doing that, we hope to increase the use of heat pump for heating application and to allow them to be used in cold region and to be more beneficial for user. Thank you for your attention.
Thank you very much for the presentation. There are quite a couple of questions left from the our discussion forum. I do have a question which is very similar as the question proposed by Liam. So moving to the lab, what would your first practical steps to develop as a defrosting method for air source heat pump?
My first practical step.
So after you complete the literature review, you have compared different technologies for the defrosting process of air source heat pump. So what will be your future research to develop? You are going to demonstrate in the lab. So what technology you are going to use in your lab to demonstrate the technology?
I will start to use I will try to integrate thermal energy storage to the heat pump. So I will need to make a design and try to make it the most simple way. Probably put thermal energy storage in series rather than in parallel. That's what I've been done. And I think I'll start with a PCM that has been widely used. I think the most widely used so far I've seen in literature is paraffin. So I'll try with that one.
Okay, thank you very much. Sorry, we are running out of time. We have to go to the next participant. Thank you very much. Okay, let's welcome our next participant from University of Aberdeen, Anna Peacock. The title for her presentation is Mapping Hydrogen Storage Capacities of UK Offshore Hydrocarbon Fields and Analyze Synergies with Offshore Wind. Thank you.
Thank you very much, Dr. Liu. Can you hear me, firstly?
Yes.
Is that all?
Yes.
Perfect, thank you. Good afternoon, everyone. I'm Anna, a relatively new PhD student from the University of Aberdeen. This research is actually going to be a collaboration between Aberdeen and Edinburgh, as it builds on some of the work I did as part of my master's thesis. We focused primarily on hydrogen storage as a means to decarbonise UK domestic heating, its storage potential in offshore hydrocarbon fields, and the opportunity to combine this with green hydrogen generation using electricity from offshore wind. So just to start, I want to touch on the motivation, why it's important. So while there's been significant progress towards the decarbonisation of electricity in the UK, which last year was 43.1% renewably generated, heating continues to be one of our biggest challenges. As you can see from the graph on the right, the percentage of growth of renewable electricity has been more than 8 times that of renewable heating since the Paris Agreement in 2015. Unlike the transport sector, which is slowly becoming more electric and hybrid driven, electrification of domestic and commercial heating would be A, extremely expensive for consumers, and B, create such a high electricity demand that we'd be unlikely to meet this entirely using renewable resources, which defeats the objective entirely. Only 6.6% of the energy used for heating and cooling was renewably sourced in 2020, and domestic emissions, predominantly from natural gas heating systems, reached 67.7 megatons of CO2 equivalents last year. That was 20.8% of the UK's total emissions. Decarbonising UK heating is therefore essential if we want to meet our net zero targets. Despite government incentives, between 2019 and 2020, there was only a 4.1% increase in renewable heat from heat pumps. And this growth rate can't achieve the emission reductions that the UK requires in a sufficiently short period of time. In the Frontier Economics report that was published only last week, which used agent-based modelling to predict consumer adoption of low-carbon domestic heating alternatives, it suggests that a move to hydrogen boilers may actually be more favourable to consumers, as it overcomes some of the critical barriers associated with heat pumps, such as the high installation costs and the kind of hassle intrinsically associated with the technology. So a key challenge for decarbonising heating is the seasonal variation in demand, which is currently satisfied by producing and importing natural gas as required. So an equally efficient balancing mechanism is essential for any decarbonisation strategy. The use of hydrogen as a green energy vector that produces no carbon emissions at the point of use offers a promising solution to this. A fully renewable electricity grid also needs to be able to keep up with demand when the wind isn't blowing and the sun isn't shining. The significant seasonal and temporal variation that you can see there on the graphs would result in periods of supply deficit, backup generation storage, we would experience a nationwide power cut, and in periods of supply surplus, when production would. A large-scale storage allows to harness a surplus, providing stability to the grid by offering short-term relief is insufficient. Now, the obvious storage candidate would be to use an electrochemical battery, a well-understood technology and highly efficient for storing electricity. However, operating facility in the world has only sufficient capacity for 100,000 homes for 4 hours. Now, this does sound huge, but on a nationwide scale, we aren't even close. Pumped hydro and compressed air energy storage, two promising mechanical storage solutions, but pumped hydro plants are very expensive and require huge areas to attain those high storage capacities, and compressed air energy storage is relatively easy. Instead, converting electricity to hydrogen via electrolysis, storing it underground, and either reconverting it to offset short-term mismatches in supply and demand, or exporting it to satisfy another demand, such as heating or heavy industry, offers an economically feasible tool for achieving our net zero targets. According to the recent IEA and IRENA reports, renewables currently occupy a 13% share of the global energy mix, with more than 1,000 gigawatts of installed wind and solar combined. However, they also forecast that limiting warming to 1.5 degrees will only be achievable if we increase the share to over 60% by 2050, which would require an installed capacity of almost 15,000 gigawatts of wind and solar. Now, such a large share will incur even greater variability, and an energy storage system becomes ever more crucial. On the right is a map from the UK's recently published hydrogen strategy. As you can see, there are already for green hydrogen in Scotland. It really is the time that we need to start to think of ways to maximise its potential. Hydrogen is also a highly promising prospect for exploiting synergies with the oil and gas sector. As good as stopping the use of oil and gas looks on paper, unless an economically competitive alternative is developed, then there's little incentive for companies to cease or even reduce production. Instead of trying to outlaw a sector that supports more than 270,000 UK jobs and contributes approximately £24 billion a year to the UK economy, decarbonising production facilities through conjunction with offshore wind, repurposing infrastructure for hydrogen transport or carbon capture, and using the vast knowledge of the subsurface to explore geological storage prospects offers a significantly more exciting opportunity for supporting the global energy transition. So on to this study. Here I've broken down our research into three key objectives: providing context for the study, assessing storage capacity of selected fields, and considering commercial application. To start, we collated non-daily metered gas demand data from National Grid for a 5-year period between 2016 and 2021, which accounts for domestic and small business use, but excludes large industry and power generation. You can see immediately the huge seasonal variation in demand, which highlights the importance of storage. The data is spatially distributed across the UK's 13 local distribution zones, which you can see there on the left. And this enables us to ensure that storage capacity estimates are geographically relevant, that the proposed geological storage sites within an economically viable distance of a demand centre offer sufficient capacity. And then just for completeness, I also had a quick look at industrial gas offtake, initially assuming that it would be a relatively consistent load throughout the year. But as you can see, it also shows quite significant variation, predominantly driven by power station offtake. Now, this in itself was quite an interesting result, as it shows that storage could also be a useful tool, although it would most likely be achieved using smaller scale alternatives localised near the demand. Both sets of data were then used to quantify the storage that would be required to meet the estimated demand in both an idealised 2050 scenario, where conversion to 100% hydrogen had been achieved, and in the slightly less ambitious 20% blending of hydrogen into the natural gas feedstock. Calculating the storage needed as the maximum interseasonal demand difference, we identified the amount of hydrogen needed to satisfy the UK's baseload and storage needs. As you can see, while the domestic and industrial baseloads are similar, the domestic storage demand is significantly greater. Now, it's this domestic component demand that we therefore chose to focus on in this study, as conversion to hydrogen technologies is likely to generate similar demand to natural gas. Using this governing equation, we used accessible field data to calculate the potential energy storage capacities of hydrocarbon reservoirs in the UK continental shelf. Basing storage estimates on production data in this way provides a realistic indication of the volume of working gas that can be stored in a particular field. The original gas in place is a function of reservoir volume, depth, porosity, and water saturation, and the recoverable gas, so the proven volume of natural gas that could be produced from a field within the techno-economic constraints of a project, serve as useful proxies for the available pore space and working gas recovery capacities. Now, I'd originally considered only gas fields to avoid the complications caused by complex fluid interactions that might occur in an oil or condensate field. But oil fields with significant gas caps, so those that have commercially produced gas in their lifetime, have a proven seal integrity that would enable hydrogen storage. So some of these have been included too. Operational fields are also included as net zero targets and mounting pressure to reduce fossil fuel production, as well as the potential impact of government incentives that promote storage over natural gas production, such as the North Sea Transition Deal, could lead to some of these fields facing decommissioning far sooner than originally anticipated. Accessible data did restrict the number of fields that could be included within the study. So a lot of field data from more recent exploration is protected under the 30-year rule and therefore couldn't be obtained. But nevertheless, work of a colleague, we've developed a database of hydrogen storage capacities for 96 hydrocarbon fields in the UK continental shelf that have a cumulative capacity of 3,455 terawatt hours. And this exceeds the calculated demand by more than 25 times. The next stage involved exploring the combination of green hydrogen produced using electricity generated by offshore wind with storage in fields. This map shows 43 existing offshore wind projects that are currently in the or early, those where it was deemed of hydrogen is more realistic. In the comparison analysis of these 5 criteria was taken to assign weightings, enabling us to rank suitable fields and identify the most optimal for coupling. I'm also currently undertaking interviews with an industry focus group using participants' expert knowledge. Weightings are both realistic and therefore provide more robust results. Operational status of the field, for example, significantly influences the business case for converting a field to storage and has therefore been highlighted as a key criterion by many of our participants from the oil and gas sector. Once complete, we'll compare these results with the original outcomes of the paired comparison analyses, which produce the following. So these 2 maps illustrate 2 different scenarios. The first on the left considers the length of existing pipeline, which could be retrofitted to support hydrogen delivery onshore for distribution around the country. And then the second on the right considers alternative export strategies, such as international connectors, new pipeline options. And while useful, the identified fields have been selected based on coupling with pre-designed offshore wind developments designed to maximize wind exploitation, not for storage optimization. So an improved methodology would work the other way around, basing site selection on field parameters that affect storage, such as reservoir formation, geochemical reactions, and cushion gas requirements, and then developing an offshore wind farm at this site. Finally, I just want to give you some key points to take away from this presentation. So an estimated 750 terawatt hours worth of hydrogen would be needed to meet the current natural gas demand. And the total hydrogen storage required would be approximately 135 terawatt hours, 120 of which come from domestic demand. The database that formed the basis for this work now contains volumetric hydrogen storage capacities for 96 UK offshore fields that have a total storage capacity of 3,455 terawatt hours. Therefore, only a few sites, most likely geographically distributed around the UK, can meet the needs of different demand centres, would be required to balance this variation in UK heating that we saw at the beginning of the presentation. Most suitable fields for coupling with offshore wind are located in the Southern North Sea and East Irish Sea, primarily due to their proximity to offshore wind developments and the coast, which reduces those the transportation costs, and the potential for exporting hydrogen to Europe makes the Southern North Sea even more even more favourable for commercial exploration. Now, obviously, this is a high-level study, so while useful for showing the big picture, if any of these sites were to be commercially developed, site-specific feasibility. And then I'm planning to use these results to influence future energy system modelling that I'll undertake as part of my PhD, looking at optimising potential synergies between offshore oil and gas and renewable sectors in the wider context of the global energy transition. So thank you very much for listening. Does anyone have any questions?
Thank you very much. This is a very high-level, useful, timely study on the hydrogen storage, which will be potentially used for the UK in the future. I don't see any people leave any question from the discussion forum, but I guess we have to speed up to the next participant. I think your study is very interesting, and you can potentially develop a very good PhD study, continue this direction into a very good research. Thank you, Anna.
Thank you.
Thank you. Okay, let's welcome our next participant from University of Aberdeen, Fiona Todd. She's going to discuss her research on impacts of heat extraction and storage in abandoned mines. Thank you very much. Please start your presentation.
Am I on? Great.
Yes,
okay,
please.
Thanks for that. I'm actually from the University of Edinburgh, not Aberdeen, but that's okay. Hi,
sorry.
Well, thank you. Welcome to my presentation, and hopefully I'll give you a little whistle-stop tour of my current research. Okay, so let me just get, as an overview then, I thought because I'm not going to be there in person, you might like to see a picture of me in an abandoned mine. So there I am standing inside a mine. And what I'm going to do today is really go through my modelling that I'm doing, and it's a thermal hydromechanical model of an abandoned mine working. And just to summarise, my supervisors at the University of Edinburgh are Chris, Andrew and Stuart, and I've also got a case sponsor, which is Quintessa, and my project is funded through NERC through the E3DTP consortium. Okay, well, I know we've seen lots of graphs about this before today, but I thought it might be useful just to give a bit of context. So renewable heat, there was a target to reach 11% of heating by renewables by 2020, and we missed that target. We're only on 6%. There was also a target, our current renewable energy trajectory is not going to reach the target of renewable energy by 50% by 2030. So what I really want to say today is that novel heat sources are going to be needed to reach this target. Now, I know Anna's just given us a good explanation of hydrogen, but I'm going to explain some other potential sources. And not only that, energy storage is needed, as Anna suggested. This will be a necessity to reach net zero. And so it's been established that storage of heat in geological systems can bridge the gap between supply and demand. And that's that gap Anna was talking about. She gave me quite a good introduction. Thanks for that. And really the seasonal storage of heat, this can produce efficient heating and cooling systems, and that will then maximize the benefits of renewable resources. So what do we need? What are the key components of heat sources and stores? Well, they need to be accessible, and that's accessible from the surface, but it's also accessible to the users. They need to have the required permeability and porosity to allow the heat and the energy to be stored. And for heat sources, if you've got elevated temperatures, these make the systems more beneficial and more efficient. So where can we find these kind of systems? Well, this is a map of abandoned mine workings in the UK, and this is just coal mine workings. And what you'll see here is that these coal workings underlie the majority of big cities in the UK. They don't underlie London, but the rest of the cities have been underlain by abandoned mine workings. And what these systems provide, as you can see from this picture, so this is a picture of some shallow pillar and stall workings where these pillars of coal were left to hold the roof up. And what you can see is this man-made porosity and permeability is allowing a potential storage system underground. So what do we need to do? Well, if we want to successfully operate these systems, what we need to have is a reliable understanding of the hydraulic, thermal and geomechanical processes. And for the non-geologists there, basically geomechanical processes are how do the rocks react to the hydraulic changes in water level and temperature and pressures that we put in this system. And this is especially important in these systems because they're anthropogenically altered. They've been dewatered to allow mining, and also they've allowed the mine water to recover. And they've also got this all these cracks and impacts to the actual mining itself. So what I want to understand is, will injecting and extracting heat from these systems cause any potential surface issues? So the way I'm going to do this, well, I have done some part of this, is through numerical modeling. Now, this is the first time this kind of model is being done for this kind of system. And so it is generic at this stage. And really what I'm trying to do is encapsulate the thermal processes. So that's injecting heat and abstracting heat, the hydraulic processes, and the geomechanics. And that provides you with a fully coupled THM model. Now, the problem I've got is that a lot of the models, there's no data that have all of these three components to try and, real world data, I mean, to try and validate my model. So what I've done initially is I made a hydromechanical model. And what I had rising mine water data. So this is real data where mine water has been rising up back to its natural level after being pumped out. And this has caused an uplift at the surface. So the actual surface of the ground is moving up at the same time. And if you want to read more about that research, I've written a paper about it. But basically what I got quite a good match between the uplift and the mine water rise. And so now what I'm doing is adding the thermal process in, and I'm going to show you some results on that. So just a quick overview of my model. As I said, it's relatively basic. It's looking at mine workings in the top 60 meters. And this is because we expect them to have the shallower mines to have more of an impact on the surface. The mine system that I'm looking at has got 5 pillars. So these black bits were, like I said, holding up the roofs. And these rooms, so these empty spaces, which I've filled with water. And in the model, I basically inject heat into these rooms and see what happens into the model. So here's an output then. I've got different heating cycles where I'm injecting 50 degrees, 20 degrees, 50 degrees, 20 degrees in a cyclical form. So this is one of the outputs of injection of 50 degrees. And as you can see, oh, sorry, get rid of my emails, that would be good. As you can see, there's heat injection there. And then this is again an example of injection at 20 degrees. And as you can see, the heat plume is not quite as substantial. I wanted to look at how far the zone of influence is for this temperature. So this is a kind of zoomed in version of my model. And what we can see here is close to the model. So this output line is within 5 meters of the workings. And the temperature changes from 11 degrees up to about 30 degrees. So really there's a big temperature change there. But this change gets significantly smaller as you expect the further you get. And 5 meters above the top of the model, really there's not really much change in the thermals at all, the injection temperature. If we look at displacement, so this is how much the ground moves to determine the temperature. And what I'm getting here is when I've got 50 degrees injection, I'm getting up to 3 millimeters of, more than 3 millimeters of displacement. And there's obviously slightly less displacement when I'm looking at 20 degrees injection. And displacement is important to look at the surface because this could cause impacts on the surface, basically. But displacement is not the only thing that we can look at. We also want to look at how close are the rocks going to be to failure. So this is not, looks like it's going to be scary and mathematical, but it's really not. So basically, if you imagine you've got your cube of rock and you've got these stresses acting on it horizontally and vertically, it'll cause a shear failure along this shear failure plane, which is here. And you can map these out graphically. So you get this thing called a Mohr circle. And really that's your stress of your rock and how it reacts. Then what you can do using rock parameters, you can figure out a failure envelope. And what we're interested in my research is how close, what impacts this blue circle, how close does it get to the line, the failure line. So we come up with a term called the factor of safety. So this is basically looking at how close the circle gets to failure. And what we understand is that a factor of safety of less than 1 means that the material is likely to have failed. And so that shows you that you're going to have an impact on the surface from these systems. So looking at my factor of safety results over time, these orange bands are where I've injected the temperature. And as you can see, it impacts, it gives you the increases in factor of safety, which then reduces and gets closer to this failure level of 1 as time goes on. And so I'm getting this overall impression. And really, this is driven by a change in the temperature. So when the temperature reduces, you're getting this reduction in factor of safety, which is what you expect. What I then did was, so this was based on my 50 degree injection temperature. I then looked at what we were doing if we changed the temperature of injection. So as you'd expect, if you're injecting a lower temperature, your factor of safety is higher. And obviously the opposite, if you're injecting a higher temperature, your factor of safety is lower. And what this shows is the increase in the injection temperature increases the likelihood of failure. Now, it looks like around these areas, wherever you're getting close to one, you might be causing some bits of failure in the rock materials. And so as we're hovering around this, it's potential that we're causing changes over time to the material. So really, the next stages of my project then, what I'm going to try and do is I want to try and identify the important mechanisms for stability. I've already had a look at the injection temperature. I'm going to look at how important is the overburden geology, how much does that affect the factor of safety? What about water level changes and the mine water geometry and depth? And ideally, I'd like to make some sort of risk matrix or map to say, this is an area where these systems might be more at risk of failure. And so maybe try and avoid these areas. And really, 3 takeaways I wanted to give you for my talk is that shallow abandoned mine workings can be used as a heat source and store. But material failure is a possible consequence of injecting heat into room and pillar workings. But this could potentially be a way of turning a risk into a resource. Now, I thought I'd have a little bit of a Christmas connection, and I wasn't quite sure where I was going with this, but what I thought was that maybe Santa Claus could use the mines that he gets his coal from to try and heat him up in Lapland, to try and keep him nice and warm. So perhaps there we go, there's my Christmas connection for you. Thank you.
Much, Fiona. How can you validate the results as you presented in your simulation? Did you validate it?
So I validated my hydromechanics, but there's no data yet to include the temperature. But I know there's some studies, real life field studies going on just now, and hopefully the timing of those studies will coincide with the end of my PhD. And so hopefully I can use the data from it. But it's yeah, right now it's not, there's no way of validating the thermal part of it.
Thank you very much. This is definitely a crucial study and important to understand the mine conversion of mine to geothermal heat recovery. I'm working on similar research as well. So thank you very much. And we have to go to our next final speaker, Ricardo Wallace, and he's going to do a presentation on injection of green hydrogen into 2D natural gas reservoir. He's from Edinburgh Napier University. Thank you very much. Please start straight away, please, Ricardo. Thank you.
Thank you very much. First of all, I'd like to take a wee moment just to thank everyone who organised this, and a little bit of background about me is I studied here at Edinburgh Napier for my undergrad in mechanical engineering, graduated in 2019, and I'm in my second year of studying the storage of gas mixtures, with my current project being the storage within green hydrogen within 2D depleted natural gas reservoirs. So I'll provide a little bit of background on that to start with. So although renewables are essential in meeting the carbon emission goals, the intermittency often results in curtailment as well as other reasons such as highly congested transmission networks, slow transmission network development, inertial constraints, and fuel price variability. And this is amounted to the curtailment of roughly 3.7 terawatt hours in 2020, costing the UK government about £274 million. And if pipeline projects are completed on time and set their goals are met for offshore, this could potentially rise to 7.72 terawatt hours, amounting to nearly over £500 million of government spending. So potential solution to this is the production and storage of hydrogen, which will be necessary at both seasonal and short-term scales. So if we look at the production of hydrogen, there's a four ways to produce hydrogen, but the main two that are considered is steam methane reforming with carbon capture and storage and water electrolysis, which when partnered with a renewable energy source is considered green hydrogen, as the production of the hydrogen is carbon emission free. What was the benefit to producing hydrogen? Well, if we look at on the right here, we can see a system produced by Air Up where hydrogen gas is represented by pink, and it's got a lot of similar capabilities as natural gas. However, again, during the production and the release of energy from hydrogen, there's no carbon emissions, which contributes to it being considered a green alternative to natural gas in a lot of ways. Unfortunately, its low density of approximately 1/8 of natural gas at standard temperature and pressure it restricts its storage at a utility scale. So subsurface is generally explored for this. There's two main forms of subsurface storage, which is engineered caverns consisting of salt caverns and man-made caverns, and porous storage consisting of deep aquifers and depleted oil and gas storage. Engineered caverns tend to be capable of shorter cycles at a reduced capacity due to stability issues. Although although man-made caverns do have potential use in the geologically limited regions where salt caverns aren't available, it sort of restricts them in a way for storage. As for pore storage, although capable of high capacities, the means of recovery will inherently result in a mixed withdrawal of fluid, which will require additional processing. So, let me just change slide. As been presented in quite a few other ones, as been presented in quite a few other presentations today, we look at the availability of hydrogen storage offshore, and we can see it's got quite a lot of opportunities. Onshore, however, this is restricted by the need for potable water and various other things, and it ends up in it being pretty much limited to salt caverns, which predominantly reside in England. A recent publication suggests that a potential 6,900 terawatt hours of hydrogen can be stored in these gas fields, and 2,200 terawatt hours potentially in deep aquifers offshore. Again, it should be noted that gas fields are good alignment with renewable wind that's been planned and projects that are in development. And the lines on the graph here, we can see that if possible, if the repurposing of the natural gas delivery systems, the NTS, is possible, then this will provide a method of delivery to the homes. So if we look at depleted gas reservoir storage here, there's some key benefits to it. One of them is a degree of sealing being assured from the geological storage of natural gas over a geological time frame. Again, the cushion gas, another benefit to this is the potentially lower cushion gas as a result from the gas already being stored, which prevents the water encroachment back into the. Another benefit is the available information on the actual storage systems from the previous petrochemical use, which allows us to know about pressure, different layers, capacities, and various other aspects. However, there are some negatives to this storage, which is, as I mentioned, the gas mixing within the reservoir, which is most likely to happen as a result of having two different types of gases. As such, we decided to investigate the injection of offshore green hydrogen with high purity injected into a natural gas reservoir. So just a bit of background on the software we use. We use our own software, which is GPS Flow, standing for General Purpose Subsurface Flow Simulator. This is capable of modeling grid-scale hydrogen and gas mixture storage within salt caverns, deep aquifers, and depleted gas fields. GPS Flow has been built upon the Tuff-free reservoir simulation software, and its primary capabilities being that it can model multi-phase, multi-component flow of single or multi-gas mixtures, including hydrogen, carbon dioxide, nitrogen, and methane. It can model these accurately between 20 and 200 degrees and up to 100 bar, with its parallelized code aiding in reducing simulation time when considering real gas laws within the reservoir. Although we currently are working with a reservoir company within the UK, we're unable to disclose any information about this due to non-disclosure agreements, and as such, we decided to look at a different reservoir to model it. We used the Rio Vista gas field reservoir model that has been modeled for CO2 injection previously by Oldenburg et al. For enhanced methane recovery. This model has been adapted to give us the anticline structure that we looked about, flipping it in, reflecting it in the z-axis to give us that formation. And as a simplification measure, all boundaries are assumed to have a zero flow Neumann boundary condition, as well as isothermal conditions being assumed. So what makes the hydrogen green? Well, the two main influences being that we assume a high purity of hydrogen, and although this is obviously possible through steam purification processes, but we use an injection rate which is based off of the offshore wind load factor, which is taken from the government websites. This resulted in an injection rate varying from 1.56 to 2.92 kilograms of hydrogen per second into the reservoir. And as I mentioned before, we've decided that we know that pore storage is best suited for seasonal cycles. So for this, we looked at the domestic usage of gas in the UK from a paper of Watson et al. From 2011 to 2012. We decided to do a cycle from March to the beginning of December for injection, and then withdrawal over the high demand period of December to the end of February. So as we can see here, the reservoir after the 9 months of injection, and a clear plume of hydrogen can be seen at the top of the reservoir, with saturation decreasing as the distance from the injection point increases. Additionally, a vertical symmetry about the z-axis occurs as a result of the reservoir's anticline structure. We know this because we tried different injection points and it creates a different shaped plume that goes towards the top of the reservoir. An interesting point is that the lateral displacement, although it's not apparent in this, is considerably higher than that of the vertical, coming to about 800 to 50 meters, which we can assume is partially a result of the buoyancy forces encouraging the hydrogen to move towards the top of the flume and the varying porosity, permeability along the X, Y, and Z axes. We can also see at the base of the reservoir here how the reservoir has been, how the pressure response in the reservoir is, with the lighter area being near where the hydrogen was injected, increasing a considerable amount more than the general gas section, and the water part of the reservoir maintaining a steady increase as well. If we look at the hydrogen withdrawal, the withdrawal was accomplished based on a master. The withdrawal was accomplished based on a mass recovery rate, and is evident from all the figures on the right that injection rate increasing considerably depletes the hydrogen plume, with 1 second still providing 1 kilogram per second still providing a reasonable shape, and then as it increases, massively depleting this. As can be seen in both the reservoir and the recovery rate on the side here in the table, the increased recovery rate expectedly increased the hydrogen recovered. However, this wasn't proportional to the actual recovered, like the total mass composition, its share in the total mass of the hydrogen of the recovered fluid, as by kilograms per second, this amounted to of all 60.48% of total hydrogen injected. This only amounted to 37.35% of the total fluid recovered, with 60% being natural gas from the reservoir. The withdrawal rate on the right here, as I mentioned, is based on mass recovery, and we can see here that the hydrogen composition in the withdrawn fluid drastically decreases as the withdrawal rate increases, with the main difference being, the highest difference being from 1 kilogram to 2 kilograms per second. And again, on the right here, you can see the effect on natural gas composition having essentially the opposite effect, with it increasing substantially. In all cases, this was evident in all cases where we withdraw. This is evident in all cases where the fluid was withdrawn. And another interesting point is that the water concentration actually decreased as the water composition in the withdrawn fluid decreased as the injection withdrawal rate increased, suggesting that the residual water within the reservoir was slowly depleting as it went. In my concluding remarks, I'd just like to say that it would appear that hydrogen storage in depleted gas reservoirs is possible, but there are some constraints which involve the trade-off between the fluid composition of hydrogen and the recovered hydrogen from the reservoir. And in all cases, this is going to require post-process separation processes to make it to make it available for the applications depending on the security necessary for them. Further works on this would be considering non-isothermal injection and withdrawal of a non-homogeneous reservoir, and then, if possible, developing this into a three-dimensional reservoir so we can understand how it works as a system rather than just as a 2D reservoir, if that makes sense. And that is everything from me. I'll stop sharing.
Thank you very much, Ricardo. We have a quick question before you go. So there's a question that says, wondering if there is a difference in the capacity of duplicated gas fields in storing hydrogen and in storing CO2. Can you quickly give a comment on this?
So I would say that it depends on the gas. It depends on the pressure you can inject the hydrogen at, because so it depends on the pressure you can inject the hydrogen at, and the limiting factor would be the cap rock's structural strength to this. I don't know about actual tons per density. I guess it's a density question about that. It would be the density hydrogen at that mass. So yeah, there's probably going to be a less amount of hydrogen for the same reservoir pressure in tons compared to CO2. If that makes sense. So you'd be able to store less tons of CO2, less
Okay.
tons of hydrogen at the same pressure compared to the same pressure of CO2. And the pressure kind of limiting factors for this, which is something that a future point for investigation.
Okay, thank you very much for everybody who participate to this session, and thank you for our 5 presentation participants, and thank you for organizing these, and Joe's as well. Thank you.